So, good evening, everybody. My name is Saida Said, and I am a PhD scholar at IIT Roorkee. And this is our eighth interactive session for the course of Geotechnical Engineering 2. Uh, excuse me. So, we will be talking about what you have studied in week 7 and a little bit in week 6. So, that is retaining walls and active and passive earth pressures. So, to recap a bit in the course, what you might have studied is wait a moment. Okay, so what you might have studied this week is uh, either you have these structures. Okay, is it audible now? Is it audible now? Okay, so as I was saying, you have these structures. For example, if you have a cantilever wall, retaining wall, any kind of retaining wall, and you have a backfill of soil here. So we are interested in knowing that what is the pressure exerted by this soil on this structure. So what you might have studied is initially there might be two cases. One case is that our wall is not moving or structure is stationary. So in that case, there is some weight that is being exerted here. Uh, we call that earth pressure at rest. Okay, now. So you might, when we study like in fluid mechanics, we talk about a fluid element below a surface of water. We say that there is a hydrostatic pressure, which means that on this element, the pressure in each direction is same. It is same in all the directions. But if you see in soil, since it is not a fluid, the property is a bit different. The vertical stress and the horizontal stress, they are not same, but they are correlated with a ratio. We can correlate sigma h by sigma v is equivalent to k, for example, a coefficient of earth pressure. Now, when the wall is not moving, we say that the structure is static earth pressure or earth pressure at rest. It's simply, there are many equations that have been given for this, but the most commonly used is the Jackie's equation. We take K naught is equivalent to 1 minus sine of phi. So, sigma V we know from it's gamma h whatever, if you have the strata and then you calculate however you calculate the overburden pressure, then at any point your lateral pressure exerted at this point will be your earth pressure times your vertical pressure. Had it been water only, then this would have been 1. But since it's not water and it's not hydrostatic, it's not equal in all directions, we take it's not isotropic. So we take this. Uh, so the thing is, here everything is very simplified. Why? Because our wall is not moving and nothing is happening. But in case wall is not 100% rigid and there is slight movement of the wall. One second. Okay, so there is slight movement of the wall in either direction. It can move here or here. For example, let me give you an example. I have a backfill here and no support here. And if my wall is not that rigid, it's going to move like this. Now, in this case, this is not as simple as the previous case. Why? Because now there is movement. So there will be, in this case, if we draw a Mohr circle and let us say, just a minute. Okay, so we draw a Mohr circle and let us say that this is the failure envelope. In case A, which is at rest, we know that there is no failure surface and nothing is failing. So this will be well below our failure envelope. For example, your Mohr circle is somewhere here. But here, as the soil is moving, what happens is that, see, here the load is applied on this wall, but if you release this fixity, I must say, so this load will be reduced a bit on the wall because like it's a bit relaxed. So that is what happens, and your active pressure vertical will be same but horizontal reduces, and to a point that your soil fails. Sorry for the bad diagram. So there will be a failure. When will this failure be there? When the soil is allowed to move. Why? Because when it is not moving, when the wall is not moving, it is like a rigid beam. There are deflections. But if you don't allow these deflection, if you don't allow this deflection, it will be it will be a force on this wall, and the wall is bearing all this force. but if the property is a little lax and it is moving a bit, so the force will be reduced to a point where this failure will take place. And now if you have a passive earth pressure, for example, let me say that soil, for example, this is filled with water and it is exerting pressure more, it is exerting greater pressure than what is being exerted here. So our wall will move like this, isn't it? In this case, the pressure from here is increasing rather than decreasing. So what will happen is this Mohr circle of failure, we will have a passive failure pressure and active failure pressure. So, excuse me. So this is what you have studied in the previous class, and then we have studied about the uh, kinds of retaining walls and the factors of safety. And today what we will try to do is, well, first let us solve a simple question on the forces on a retaining wall, and then let us talk about the factors of safety that we can calculate for our rigid retaining walls. And why I'm saying rigid is because flexible retaining walls are totally a different concept. We get sheet piles, we get bracings, we get even cofferdams. So those are flexible structures, but rigid usually are of two types, that are gravity and cantilever. So let's move on to our first question for today. We have been given a retaining wall and we have to calculate the active earth pressure occurring uh, after the occurrence of the tensile crack in the retaining wall. See, the upper part is a clayey soil, and you know that in clayey soil we will have a negative uh, force, negative earth pressure initially until the tension crack is developed, and then we get the actual forces in the active case, not in the passive case. So let us try to calculate that. So for the upper layer, Ka will be equal into 1 minus sine phi over 1 plus sine phi, which is equal into 1 minus sine 20 plus 1 by 1 plus sine 20. This comes out to be 0.49. So now let's calculate the depth of the tension crack. It is equivalent to 2c dash over gamma root Ka. It will be equivalent to 300. Make a note of the units given here. This is pound per feet. So yeah, it could not have been kilometer per meter square. That would be strange. 300 kilometer per meter square. So this comes out to be 7.8 feet. This is the depth of tension crack. But here, as you can see, the depth of clayey soil is only 2 feet. So tensile crack will develop only up to 2 feet. It will not go on to develop inside this sand layer also. It will only develop up to 2 feet. So let me write since depth of clay layer is 2 feet, which is less than 7.8 feet. Tension crack will develop only up to 2 feet. Okay, so at at z is equivalent to 2 feet, sigma naught is equivalent to sigma naught dash, because there is no talk about any water table here, and this is equivalent to 2 into 110. Now see what will happen. This clay soil, it will not show any resistance or any active earth pressure resistance. It will not show that, but the weight of the soil will still remain there. So what we do is we convert this weight, uh, because it is not showing any resistance, it is not of our use in the resistance diagram, but it still has some weight. So we convert this into a UDL or surcharge. If it is H and gamma, we will have a surcharge load over our main soil, which is here. What? Wait a moment. Yes, yes, yes. Mm. As I mentioned, as I mentioned that depth of tension crack is 7.8 feet, but our clayey soil is only 2 feet. So we will take our depth to only 2 feet and not more than that. Because even though our whole depth is 5 feet, tension crack will not develop in sand. You understand my point? Yes, because tension crack will not develop in sand. This is a property only of clay soil. Okay. Sand, it will not develop. Na? This, why does tension crack develop? You see, in cohesionless soils, you have a proper K. You remember? Cohesionless soils, cohesive soils. Yes. Okay. Now, I was, as I was saying, we will get a sigma naught equals 220 feet. So, sigma active will be equal to uh, did we calculate the second? Did we calculate the one second? Okay, this is for the first layer. Let's calculate for the second layer. Uh, this will be 1 minus sine 30 by 1 plus sine 30. This will be to 1 by 3. Okay, so now this is our soil, and let us say, as I said, that we will replace it by a surcharge. Q is equal to 220, and if we draw a diagram for this now, sorry, let's draw the earth pressure diagram. I'm really sorry. Um, let us. So we will have a k a 2 times q, and then here we will have k a 2 into gamma 2 into total height minus h1, we can say, if this was the clay layer and this is our sand layer, and we have replaced this clay layer with the, yes, this is not sigma a, sorry, sigma naught is surcharge, overburden. Ah, at this level, at z is equal to 2. This is lb, pound per feet square. Pound per feet square. This is a different, this is not metric system that we are used to. This is FPS system, feet pound second. We use MKS system. We use meter, kg, and second. And this is some of the Western countries used. The question example that I'm taking from, they have used the FPS system. That is why I did not want to change the either I could have changed the values, but I thought let us move on like this. Okay. Small q, as I said, that this clay will not we will not uh, this will not give any stress to the wall because of a development of a tension crack, isn't it? So, but it will have a vertical component. This is pressure. Yeah. Okay. So we have converted this to a load, and can you calculate these values, Vanita? Uh, what is different? Don't think about the units. Let this be. We don't need to change anything. Let this be whatever we are used to. It will just have to be multiplied by a factor. It doesn't matter. Units don't matter here right now. What I'm saying is that, do you understand that we convert this into a surcharge, and then surcharge will be then there will the load, this surcharge at the bottom, there will be Ka2. Ka2 is 1 by 3, 220 by 3. So we will get here, it will be 73.3 pound per feet, and at the bottom it will be 1 by 3 into 100, 220. plus gamma 2 is equal to, how much is gamma 2? 108. 108 into 3. So this will be 181. Let me assume, for your sake, let us assume that this is kilonewton per meter square, even though the values are not appropriate to change directly. I would have to reduce them, but let us not. Okay, let's do one thing. Yeah, yeah, yeah. Please, please, please mention. Yes, Vanita, I'm listening. Where, where? Bottom of sand. Okay, okay. So, if you calculate at top, you will get K82 times Q, which will be 1 by 3 times 220, which will be 73.3, I think. And then at the bottom, it will be Ka2Q plus Ka2 into gamma 2 into total H minus H1. Uh, if this is the clay and this is H1 and bottom is the sand and this is total H, so this is equivalent to 3. This will be 1 by 3, 220 plus 1 by 3 into 108 into 3. Is that right? This will be equivalent to 181. Yes. Yes. See, why we have calculated the depth of tension crack? Because the pressure exerted is only after the tension crack. Something like this, isn't it? Something like this we have in cohesive soils, active pressure, isn't it? So if our wall, if the height of our clay layer is somewhere here, so this part is not even getting materialized, not acting on the wall. So we're not taking that. That is why the question asks occurrence of tensile crack, determine PA after the occurrence of tensile crack. So see what happens is, visually if I show you, uh, this is my wall that has moved, and this is the clay soil that was there. There is a development of a tensile crack. So what happens is, let's let the crack be here. what happens is, due to this detachment of this solid body, the load was uh, produced by this, due to this detachment now, now this load is not getting carried away here. This is what a tensile crack means. Do you understand that? Are you getting my point, Vanita? Are you getting my point? See, in a continuous system, if there was no tensile crack, all this material was exerting its weight load here. But now the tensile crack has developed at the top, for example, till here. What happens is, this portion gets this portion gets detached. This portion, this is the depth of the crack, and this portion gets detached such that this height of the soil stops. Due to this discontinuity, this height of the soil will not now uh, produce its load or provide its load to the wall. So this is the tensile crack. So what happens is that this becomes inactive, this portion, and from below this we calculate the active pressure. Do you understand what I'm saying, Swanata? Okay, so because here this value was lower than the depth of the tensile crack, which means the whole of the clay layer will not take part in providing this pressure here because of detachment from the whole body. Okay, so that is this question. That is it for this question. You got the okay. Uh, you got the value of pressure above, a value of pressure below. The diagram, let's calculate the total pressure now. Still not what I want. So let me do one thing. Actually, it would be better if I insert two shapes. It will serve our purpose better. Okay, so let us say let us give another color to this. Okay, so this is 73.3 pound per feet square. And this, oh, this comes out to be 181.3, and we know the height we are taking is only for the sand, because we are not considering the clay here. So this will be 3 meter. Can you calculate the area of this diagram, Vanita? Vanita? Let's calculate the area of this diagram. This will be, the force will be equal to this will be equal to 381.9. So finally, our solution is PA equals 381.9, approximately 382 pound per feet. Is that okay, Vanita? Can we take a little break? Okay. So this was the first question. Now let us move on to the next question. Before that, let us talk about a little bit about the stability of our. Yes, Vanita? Yes? Yes? Yeah, that is the question. We answered the question. This is what was asked here. Determine PA after the occurrence of tensile crack in the retaining wall. Okay. Is that fine, Vanita? Okay. So, the essential steps in determining the stability of rigid retaining walls. Uh, First of all, we calculate the active lateral earth forces and its components. If the wall is smooth, we use the Rankine's equation because they are simpler than Coulomb's equation to calculate the active earth pressure coefficient. Uh, okay. Then we determine the weight of the wall and the soil above the base, as in if uh, there is some embedment or the cantilever, this weight of the soil and weight of the cantilever and weight of the soil, they are resisting forces, so we calculate these. Then we determine the factor of safety against translation, then against overturning, then we check for the eccentricity, and then we check for the tensile crack at the corner, ultimate bearing capacity, and this is how we do the stability analysis. So let us do a simple stability analysis. Uh, just give me a moment. Let me take a simple question. Okay, let me draw this retaining wall. One second. Let me take this question. Okay. This is phi dash CS. Gamma saturated 30.8 degrees. Okay. And existing soil below the base has these properties. So Vanita, where should we start with this question? This question on our where should we start? Is it okay? Uh, this is kilonewton per meter cube. Okay. Uh, this is how you have calculated the phi. Let's just take it as phi dash. It refers to the method you have taken to calculate phi, and that's not. Yes. Where phi equals. Okay. So how do we start this question, Vanita? Yes. There are not two layers. Basically, gravity retaining wall is shown here. Let me show it here. Gravity retaining wall is shown in figure. Is required to retain 5 meter of soil. Backfill is coarse grained soil with gamma saturated. So if the backfill is different, so we will have a let me say uh, insert a shape here. So we will have a soil here, um, coarse grained soil. Okay, isn't it? So this will be our backfill. And initially, the soil that was present there, which will be this. Okay. The existing soil below the base has the following properties. Gamma saturated is 20 kilonewton per meter cube. Phi dash is 36. Let me just write phi dash, okay? And here also, let me write phi dash. Okay. The wall is embedded 1 meter into the existing soil and a drainage system. Let's forget about the drainage system for now on. For now, okay. The groundwater level is 4.5 meter below the base of the wall. Determine the stability uh, of the wall for the following conditions. Delta, it is taking 20. Okay, that is the angle of friction for the wall is taken as 20. So can you tell me now how we proceed? Let's go back to the previous slide. Yes, yes. So what we do is first we calculate the active lateral earth force and its components. If the wall is smooth, we use Rankine's equation. If the wall is rough, then we use Coulomb's equation. So there are three conditions for this. Two conditions. Wall friction is zero. That is 1 second. We have to calculate uh, conditions for one smooth wall or rough wall. Okay. यहाँ पे we will have a delta equals to 0. Okay. So our first point only says that we use Rankine's equation if the wall is smooth and Coulomb's equation if the wall is rough. Then we determine the weight of the wall and the soil above the base. In this case, there is no soil above the base. Soil above the base is more relevant for cantilever type system in which we have a overhang like this. Then we calculate this weight because it is resisting weight. Okay. Then we determine the factor of safeties. Okay. So let us do that. For case 1, we will have Ka, let's say Rankine, equals 1 minus sine 30 over 1 plus sine 30. This will come out to be 1 over 3. And let's calculate for Coulomb also. For Coulomb, delta is equivalent to 20. Since there is no incline in the loading, we can say beta is equivalent to 0. Okay, so let's calculate. Let me refer to this Coulomb's equation. Okay. And since the inclination of back of wall is also 0, so our equation for is according to Coulomb, it becomes let me write it in a better way, please. Mm-hmm. No, not on the black fill because see what we will maybe check that for the bearing capacity or deep-seated failure, but for the anything above the soil, the black backfill, the gravity, it is of no consequence. And this comes out to be, let me write, RK A Rankine is equivalent to 1 by 3 and RK A Coulomb equals 0.3. Okay, so let's determine this was step 1. Now for step 2, determine the lateral forces. Okay, so for Rankine PA Rankine, it will just be a triangular distribution. This will be Ka sigma naught. This will be H. Half of KAR gamma H naught square saturated. I think was given in the here gamma saturated 18. This will come out. This will be 1 over 2, 1 over 3, 18 pi square. This come out to be 75 kilonewton. And this will act horizontally because ground surface is horizontal, and it will act at 5 by 3 from the ground of base. Okay, and for Coulomb we will get half of KAC gamma sat H naught square 1 by 2 0.3 into 5 square should be equivalent to 67.5 kilonewton. Okay, but this will act where uh, this will act horizontally for case 1, or if we are taking friction as 20, uh, sorry, for Coulomb we are taking friction, so it will not be acting horizontally, but it will be acting at an angle of 20 degree to the horizontal. It will be acting like this. Okay, so this will have a horizontal component and this will have a vertical component. This will be PACV, PACH. So PACV equals PAC sine delta, PACH equals PAC cos delta. This will be equivalent to 67.5 sine of 20, which will be equivalent to 23.1 kilonewton. This will be equal to 67.5 into cos 20, which will be equivalent to 63.4 kilonewton. So we got the components, horizontal and vertical components of the lateral forces as discussed in the previous slide. Okay, so if we draw a diagram, force diagram, we will have a, let me take this. Okay, so let this be the wall. We will have, yes, here, here. Okay, this is 0.6. Let me first insert some. So you will have a, sorry, we will have a horizontal load. There will be the Rankine's load. We will also have, this is for case 2. Both of them will not be acting on the same. Let's actually draw two diagrams to, uh, so that we don't get confused. So this is for the Rankine. We will have a load like this at h by 3, and this is for the coulombs. Okay, this will be at 20 degrees. So this will be at 20 degrees here. Okay, so now this is for Rankine and this is for Coulomb. Let's calculate the weight here. This will be W1. And let's calculate this individually. This will be W2. And from the diagram, we know that this is equivalent to 0.6 meter. The height is 5 meters. And this is 3.6 meters. Okay, same goes here. And let us take this as our axis or datum. Let's take this as our datum in the vertical direction and base as the datum in the horizontal direction. And we will also be calculating the distances. W1 will be at, I don't know why this happens. W1 will be acting as at 2.5 meter above the base. W2 will be acting at 5 by 3 meter above the base. And the distance of the centroid from the x, let this be x2, and this will be obviously 5 by 3 plus 0.3. Let this be x1. Okay, so now Rw1 equals, let this be B1 and this be B2. B2 into H into gamma of concrete, for example. This will be 5 into 0.6 into 24, which will be 72 kilonewton. W2 equals half of B1 into H into gamma C. This equals half of 3.6524. This will be equal to 216 kilonewton. So the total weight will be W1 plus W2. See here, we are not calculating any soil weight because because of the shape of the wall, 288 kilonewton. Okay. Now let's calculate the locations of the resultants. Let this be the overturning point that we want. Okay. Let me show it on this. We know that from the base, this will be 2.5. And this will be 5 by 3. This will be 3.6 by 3. That is 1.2. And because this is 0, this will be 0.3. This will be 3.6 plus 0.3, 3.9. So these are the x and the y distances. Let's now calculate for now we want to calculate the wall stability. So we will calculate the overturning moments. Let me duplicate the slide. Oh no. Yeah, sure. We know that moment for overturning is equal to W1 into X1 plus W2 into X2. See, because they are acting like this, and this moment we multiply by this distance. Acting like this moment multiply by this distance. And now we have acting like this, and for it to turn, we multiply by this distance. For Rankine, we will multiply, and we are taking this as positive and this as negative. No, no, no. We are taking this as positive because this is the direction. So we are taking this as negative. Okay. So this is the direction for this. So it will be minus PAR Z bar A. Z bar A we have already seen. Uh, Not actually already seen, but we will calculate. And the horizontal load is 288 kilonewton. Vertical load is 288 kilonewton. The resultant of the forces, just a moment. So this is the resultant from O, moment by vertical load. We are getting the resultant from this point of the forces acting. And for Coulomb, we will have m naught is equivalent to w1 x1 plus w2 x2 plus paz c into the whole base, because as I said there will be a horizontal component and a vertical component. So this will be acting here. Okay, so this will be into complete base minus uh, horizontal. Let's say V. Let's say V. Okay, so the horizontal load will be acting at ZA by 3. Uh, 5 by 3. Let's write that AC. This will be equivalent to 72 into 3.6, 0.3, 216. This comes out to be 790.6 kilonewton, and we know RZ equals W plus. Are you? Is it getting too jumbled? Vanita, is it getting too jumbled? Yeah, is it getting too jumbled? Let me write the formula and then, yeah, are you getting it? So this comes out to be 790.6 kilonewton meter, and R we W plus PAV. So our X bar C will be M naught over RV, which will be 2.54 meter. So here we get 2.34. In the Coulomb case, we will get 2.54. Okay, moving ahead. The base resistance is equivalent to the vertical load we used to do that in friction n tan phi. The used to be n tan phi. So that is what we use here. A vertical load into tan of the whatever is at the base, because that is what is uh, resisting the translation movement. So we need the internal friction angle of this material and the load on this material. Phi base, let me write. So this will be for Rankine 24 degree, and for Coulomb this will be tan 24 degree. This will come out to be 128.2 kilonewton. This will come out to be 138.5 kilonewton. So this is the base resistance against translation. Okay, so factor of safety against translation for Rankine will be 128.2 over 75, because this was 1 second, this was the where did it go, weight, total weight, not the total weight, but the 75 here is, give me a moment, PAR, the lateral load. Let me write it here. I got confused. This will be T R by PAR equals 128.275, which is 1.7, which is greater than 1.5. So satisfactory. Factor of safety for translation in Coulomb will be TC BAC equals 138.5 over 63.4, because that is the vertical, sorry, horizontal. Hmm? Yes, because if we go to the question here, it is taking, okay, it's taking 36. Let's say that this is 5, here is 24. Okay, okay, let me change this to 24, because that is something not relevant here. Yes, yes, yes. There was another calculation for it, but it is not relevant here. Okay, that because it was 5p and 5cs, and then we had to calculate the 5cs. Okay, friction is, yes, 36, 36. Yeah, yeah. In the at the base. Okay. So this is the translation. Now rotational stability for Rankine, our E will be B by 2 minus x bar